Today we're going to finish the integration of our Zestek flappy paddle steering wheel hub, as well as get some data flowing to our CANChecked display. In the first installment, we designed a custom PCB that's supplying the car with LIN bus messages so I can drive without getting a bunch of cruise control errors. Now we need to get the thing connected to the CAN bus, so let's dive right into that now. We need to disassemble the steering column to gain access to the clock spring. Here there's 6 pins for the airbag connector, but only 4 of them are used. This means that after we verify continuity, we can then repurpose those to pass our CAN bus signals through. Almost all of BMW's connectors are TE Connectivity MQS series. It's very easy to get terminals and then add circuits to the harness. Next, I need to remove the shifter assembly because this is where we're going to tap into the powertrain CAN bus signals on the car. For the shifter side, we sourced a new, totally legit, not counterfeit at all connector from AliExpress. The car's CAN signals are fed into a custom PCB that I designed. It's just a simple STM32 with 3 separate CAN channels. This is going to allow us to pull data off each of the powertrain CAN buses, do any required math or conversions, take those signals and then broadcast them to our EMU CAN bus. As with all my custom electronics, these were manufactured and assembled by JLC PCB. I also use JLC's 3D printing services to have the custom enclosure printed in SLS nylon. As always, the parts were high quality and the turnaround time was about a week and a half. If you have any custom PCB requirements for your own project or want to have something 3D printed in nylon or even stainless steel, head on over to JLC PCB or jlc3dp.com. I have links in the description as well as a discount code to save a few bucks off your order. Next, we're going to need a spot where we can connect our data logging or tuning devices to the CAN buses. We broke out the Einstar Vega 3D scanner. Using HD mode, I scanned the area in the console that we're going to use for the model. All of this took less than 5 minutes, processed the scan on the device, and only had to import it into Fusion to start working. Basically what we did here was to create a giant connector housing that serves as an insert into the console. This gives us a nice clean access point that's out of sight when we're not using it. To design the part, I made a series of mesh section sketches and then just lofted them together, added a few fillets. For the connector portion itself, I downloaded a model from TE Connectivity, simplified some of the features a little bit, and then sized the holes accordingly for the pins. Last is a Y connector that's going to house our terminating resistor, as well as serving as the branching point for another future controller. To test everything out, I had to fix a small error in my original code where the horn wasn't working. With a quick one-line change and uploading the code over our CAN bus bootloader, we now have a functioning horn. If you're going to CAN bus in any sort of serious capacity, you're likely going to end up with a bench full of various devices, ranging from the cheap Amazon-style pieces of garbage, which work most of the time until they don't. You waste a bunch of hours troubleshooting a bunch of trash, to devices that you might manufacture yourself, such as this, which is basically just a dual-channel STM32 based device that I do a lot of testing and troubleshooting for some of the code that I write. Then we have our higher quality retail devices, such as this one from Peak. I really don't like these because they're kind of expensive at 300 bucks, and all it gives you is a single channel CAN to USB interface. But there are a lot of products on the market that use the proprietary licensed Peak firmware interface, whatever you want to call it. And one of those is the ECU Master EMU Pro that I'm going to use. While they do offer their own USB to CAN device, which is much more affordable, by the way, it is also compatible with the Peak device. And the Peak device is also compatible with Linux CAN socket and all that stuff, so I can flash my own controllers with a CAN bus bootloader. So it does offer a level of usability and convenience, but that's where it ends. Next, we'll talk about what is probably my favorite manufacturer of CAN bus devices, and that is CSS Electronics. The CL1000 was the first product that I bought from them, and it's a single channel CAN to USB interface, but it also has a built-in SD card so that you can data log those files and then go back and look at them later. Really usable, and this has been my go-to for a long time for both data logging and just live CAN bus streaming. But finally, we have the most important piece of CAN bus hardware for this build, and this is a newer device for CSS called the CAN mod router. I think it came out last year, maybe the year prior. But this is a device that allows you to stream 4 CAN channels at once to a single USB, and then do all your data logging and capture all of that into a single file that is all time-stamped, and you don't have to go back and realign everything after the fact. Being able to stream and sync 4 CAN channels is going to be hugely beneficial to this build because BMW has 2 separate CAN buses for their powertrain system. I'm going to have my own EMU CAN bus that I'm going to have to log and deal with, and then finally we're going to be able to connect to the OBD2 port at the same time. There is one thing that I absolutely hate about the commercially available retail devices is they all feature DB9 connectors. And I realize that it's the industry standard, but come on guys, it's 2025. Standards change, let's move on. The fact that we've got a DB9 connector to some DR25 over TFCell to a Deutsch DTM connector is just kind of a comical situation. Before we go too much further, if you're new to CAN bus and want to know the basics, what's a bit, what's a byte, how to make your wiring connections, definitely check out the course by High Performance Academy. They do a really good job of breaking it down into digestible sections to help guide you through the process of learning all about CAN bus. They integrate some real-world examples of setting up aftermarket hardware, as well as doing some reverse engineering. Check out the direct link to their CAN bus course via the QR code here, or check out the links in the description with a discount code for that as well. So we've got an access point to the car, we've got hardware to connect to it, now what? We need software to be able to data log our CAN bus signals. My go-to for that is SavvyCAN. It's an open source free software that's really powerful and has a lot of tools for reverse engineering. It gives you various ways of visualizing the data, seeing what bits and bytes are changing, as well as being able to graph them and give you a visual representation of the data. If you're going to be using any of the products from CSS Electronics, I recommend downloading SavvyCAN from their website so you know that the build version of that is going to be compatible with their latest hardware. So we're connected to our SavvyCAN software. We're utilizing all 4 channels of our CSS CAN mod router. We're connected to the OBD2 port, and because in the configuration file for the CAN mod router, we can set it up to send messages, we are going to be requesting the RPM signal over OBD2 so that we can use that trace and correlate that to the native powertrain CAN bus data. So we're utilizing our new access points, and only thing left to do now is to go for a quick drive and collect some data. Now that we've collected some data, you're gonna wanna be able to decipher those messages. If you're lucky and working on a platform that's largely popular, you might be able to find a DBC file that already exists. A DBC file is a text file that contains all the definitions of what the CAN messages are and the signals contained within those CAN messages. It goes a step further to define what the scaling and offset is of those messages. One of the largest collections of DBC files that I've found to date is in a GitHub repository, and I will link to that in the description so you can check it out there. DBC files aren't really that readable on their own, so we're going to use a software from Vector called CANDB++. This free software allows you to create and modify DBC files. You can easily add CAN messages and then the signals that make up those messages. Here's an example where you click on a message, it'll bring up the signals that are contained within that message. You can easily see the size of the data pack as well as what bit in that message that the data starts. Clicking an individual signal brings up additional details such as the scaling or the offset. In the case of RPM here, it's multiplied by 0.25. One of the features that I use most often in SavvyCAN for identifying possible CAN bus signals is the frame data analysis tool. Basically what this does is gives you a visual representation of the entire CAN message, and then we'll graph the data that's in each byte. This makes it easy to identify possible valuable data. The other feature is a heat map that identifies which bits are changing faster than others. Bits that change the most are going to be a warmer color, and those that change less often are going to be a cooler color. The key here is that most CAN messages are going to be either 8 bits, 12 bits, or 16 bits. So for example, in this heat map, you can see starting at bit 28 and spanning to bit 39, that is likely a 12-bit message. Likewise, bits 5 and 6 probably contain a 16-bit message. We're going to cheat a little bit here because we already know what the signal for RPM is. We're going to bring up a graph of RPM from our OBD2 trace. An important signal like RPM is likely going to show up on a numerically low CAN bus ID number, which is going to give it higher priority on the bus. Because it's a 16-bit signal, we're going to search for a span of data that looks like it covers 2 bytes. In this case here, we're going to make a graph of bytes 5 and 6 on CAN bus message A5. Then you can see that that data graph exactly matches that of our OBD2 trace. Although you can see on the side that the scaling is wrong. If you get lucky, the scaling and offset will match that of the OBD2 message, so we're going to plug in 0.25 here. Now we have a completely identified RPM signal, and you can see that the resolution is quite a bit higher than that of the OBD2 trace. So what you're going to do is systematically go through your CAN messages and identify anything that looks like it might be interesting. Find a range of data that looks like it has regular activity and it has a graph that looks like it's a reasonable signal. Then you can go to your DBC file, add a new signal. I'll just name it as unknown and make note of the message ID that it belongs to. Then likewise, I'll create a new message and then add that signal to it. This way in the future, once we identify what that is, we can simply go back and modify it. Here, let's use our previous example of OXA5. And if we search, we find a forum thread of somebody that seems to have had some CAN bus wiring damage, and he posted the entire list of fault codes that came up. You can see here where BMW did a fantastic job of identifying what the message is, what the sender is, and what the receiver is. This doesn't necessarily make things easy, but it at least points you in the right direction of what to start looking for. So we've gotten to the point that we've got CAN bus messages, we've got some of the data decoded, but now we've got some custom controllers that we need to program. If you're new to this, you might be tempted to use the Arduino framework for programming.
It's a trap!
On the surface, it's a really user-friendly platform that allows beginners to quickly get kickstarted on their project, which is great if you're using something like an RGB LED panel or something like that. If you're going to be doing a more complex project, especially driving controllers in an automotive environment, I suggest that you dive in and learn how to program in C. While Arduino really isn't a programming language, it's just a layer of C++, it's built upon a number of user-generated libraries for all sorts of different examples. At face value, this might seem great because you can find a library that does what you want it to, but if that doesn't work, it incentivizes you to just go find another library, and if that doesn't work, go find another one until you have something that does work. The problems start to arise when you start combining different libraries and need to take a deeper dive to start debugging why something isn't working. Then you realize that those libraries are built upon other libraries, which are built upon other libraries, and it's sort of like this big pyramid scheme of questionable code. If I'm going to spend a bunch of time debugging bad code, I at least want to know where the source of it is. So if we're not going to be using the Arduino environment, then what you're going to be programming in is going to be dependent on the hardware that you choose. and almost all of my projects use STM32s as the microcontroller. STM32s are hugely popular in both the professional and the hobbyist space, and there's a ton of examples provided by the vendor that can allow you to get started very quickly. ST Micro has a range of development boards called the Nucleo series, and it has the microcontroller, the programmer, and usually some buttons and LEDs, so you can very quickly get started for about 20 bucks and decide whether or not this stuff is for you. It's very easy to get started and then follow some of the included examples. The only time that I don't use STM32s is if I need Bluetooth or Wi-Fi connectivity, such as the time that I designed a Bluetooth touchscreen head unit for my old E30. Just like STM32s, ESP32s are widely used in the professional industry as well. If you look at this OBD2 adapter from MHD, if you look inside the translucent housing, you can see that it uses an ESP32 as its core microcontroller. For this build, none of my controllers are going to use wireless connectivity, so we're going to stick to STM32s. To start the project, I'll use their software called CubeMX, and then do all the final coding in Microsoft VSCode. With STM32, you're going to start your project in CubeMX. It's going to give you a visual representation of your microcontroller. You can set up all your communication peripherals such as LIN bus or CAN bus, set your CAN speeds, and then configure all your inputs and outputs. If you want to change a pin, you simply click on it, and here we can change this into an output. If you decide not to use it, then you can just simply put it back to the reset state. After everything's configured, you hit the button Generate Code. It's going to generate all of this code for the startup and initialization of the peripheral, so you don't have to. You will need to set some of your CAN bus filters, but this is all just copy and paste from online examples. One of the main reasons that I like to use VS Code is its IntelliSense autocomplete features. If you want a for loop, just type for and hit tab. If you want a switch case, just start typing switch and then hit tab. Even something as simple as an if statement is a time saver. As you start typing the variable that you want to base the condition on, it will automatically pop up a list to choose from. When it comes to writing and structuring the code, I typically use one of two approaches. The first of which is event-based. If we receive a CAN bus message, we process it and do something with it. If we receive a LIN bus message, then we take some action. Likewise, if we have a button pressed, we can do another thing, or if we have, say, a sensor and it exceeds a particular threshold, then we can trigger an output. The benefit of this is that you're not bogging down the microcontroller's resources, and you're only using it when you have an event. This means it's a little bit easier to add additional functionality down the road without compromising your existing code. Let's take a look at an event-based response to a LIN message request. We have a switch case that allows us to respond differently based on the message. In this case, the first thing we're going to do is make sure that the power to our steering wheel is on. We have it set to automatically turn off if it stops receiving LIN messages. Then we got to start filling up our data transmit buffer. Byte 7 in all the data logging was always the same, so we're going to set that value to OXC0. In the first video, we discovered that if we pressed the volume button up or down, it would change on data byte 2. If we pressed it up, it would send OX08, and if we pressed it down, it would be OX04. So here, depending on what we want the car to see, we'll then fill byte 2 of our transmit buffer. If we want to change the state of any of the other buttons, we'll just add them to their respective transmit buffer locations. There's also a counter that goes from 0 to 14. We're going to have to increment that on byte 6. Byte 0 is a CRC8, which is a form of data validation. And just like most of the stuff, the code for this is pretty much just copy and paste from examples that you'll find. Finally, we add our LIN bus checksum and then transmit our message. The last thing we do before we exit the function is to increment our counter, or if we're at 14, reset it to 0. The second approach is to use a middleware called FreeRTOS, which is short for Free Real-Time Operating System. There's a lot of features in this that I don't really utilize to their fullest, but I typically use it as a simple scheduler. Basically, in FreeRTOS, you create a number of tasks, and I create those tasks based on the interval in which I want them to run. I have things that run at 10 milliseconds, 100 milliseconds, 250, so on and so forth. Again, this becomes a strategy of being able to limit the processing of the microcontroller and only handle things when they need to be handled. There's also additional benefits to the FreeRTOS, like preemption. So if you have a more important task, you can have it automatically override a less important one to make sure that it executes immediately. Even when using FreeRTOS as a scheduler, I still have event-based actions such as this, where I have a switch case that, depending on what the CAN message ID is, it will handle the data differently and assign that to the respective variable. Likewise, when it comes to sending CAN messages, I create a function that contains all the messages that I want to send at that specific interval. This way I can send critical messages more often than those that are less important. So we've got all of our data logging stuff disconnected, and we've got our CAN gateway programmed. We've got our CANChecked screen all set up, and you'll notice that it's off right now. I did integrate some power switching to the screen. This way its default condition is off. So if we just click the switch, it'll turn on. So we've got our CANChecked screens configured more or less as a temporary basis. Eventually I'll try to do some gauges that are kind of reminiscent of the OEM setup, but we just have some easy to read data right now and different screens. So here we've got our water temp or oil temp, high voltage battery voltage, high voltage current, and then high voltage battery temp. I also have a couple other screens. This is a touch screen, so you can just swipe. And to simplify it a bit, we've got our high voltage, current, and temp again. And the reason that I want to focus on this stuff is to understand how the hybrid system interacts with the internal combustion, when it's charging, when it's discharging, how much it's discharging, so that we can appropriately apply some of those strategies to our 13B swap. The other aspect of why we focused on RPM was our Zestek CAN bus hub has a built-in shift light. So we wanted to get that functioning and tie RPM into it. So with everything working, I guess let's just go for a quick test drive and see how all this stuff functions. So one of the things that you might have noticed is that the high voltage current is significantly lower in first gear than in second gear. So they're doing a huge torque derating, which I think if we can fool the car into supplying full torque, we should be able to get some decent acceleration and more importantly, some maybe all-wheel burnouts. That could be kind of cool. So that's kind of it. It all just works. We're gonna have to add some more data signals to the screen as those become available. And then obviously once we actually perform our 13B swap, then we're gonna start integrating functionality to all these switches. We're gonna have some multiple selectable options for boost control and traction control, different drive modes. So I think for now, we're just gonna enjoy our newly working data stream and our shift indicator. So that's about it for this one. I know we covered a lot of ground, talked about a lot of different stuff, and really only glossed over the surface of some of it. If you want to know more about any of this stuff, I'm going to have a ton of links in the description, so definitely check those out if you want to know more. As always, if you made it this far, thanks for watching. In the next episode, we're going to take a look at possible alternative engine swaps for the BMW i8, particularly if we throw the hybrid system in the trash and free up a little extra room. So we'll see you next time.